Hey guys, today we're going to look at projectiles launched at angles. So in the past video we looked at them just launched horizontally off of a cliff or a table. Now we're going to look at launching them at an angle into the air before it falls back to the ground. This diagram on the right is a motion map of what the path of a cannonball looks like for a projectile that is launched at an angle. How do they relate to a projectile that is launched horizontally? If we notice, these distances are the same again, just like they were in the last video. So our horizontal motion is constant, just like it was in the past. And if we pay attention to this direction, we have a small distance, a larger, and an even larger. So our vertical motion is not. They are still accelerating. So those are the same as before. But how does this path differ to the path that we saw in the last video? It differs because we are now traveling up to a peak and then falling to the ground. This is just a little bit after half of the flight path. If we had a more distinct example, it would look like this. So we travel up. This is the point where our horizontally launched projectiles begin and then travel back down to the ground. So it's now a full parabola instead of just being half of a parabola. So what do we know now? The components of the velocity have the same relationships. The horizontal component is always the same. The vertical component changes. But now we have a resultant, or a diagonal, of the rectangle being formed. Now the one thing I don't like about this diagram is that it's not drawn tip to tail, which I told you had to do in previous slides. So instead of this red arrow being here, I would actually have it being here. So we have the tip to tail method for the two vectors of the triangle, as well as the resultant. In addition to the fact that we now have both directions of motion, an upward motion and downwards motion, time is no longer the same in both directions. The x time and the y time have a relationship, but they are no longer directly equal. So this path of a projectile, the object is going to follow and go up to the top and then fall back down to the ground. So now time in our x direction is always 2 times time in the y direction. So time in the x, this entire path is actually twice as long as it takes to get to the maximum height. And at the top of this path, we have another piece of information. For a millisecond, our velocity is 0 meters per second. That projectile hangs in the air without moving for a split second before it falls back down to the ground. Now, whether we use that as the initial velocity or the final velocity is up to us for a specific problem, but we know that at this point, the velocity has to be 0. So how do we use this to calculate unknowns? The first step is to break the initial velocity into the horizontal and vertical components. So we're going to be using trig, whether it's sine or cosine, to do that. The initial velocity of the projectile is kept the same. Changing the angle of the projectile will affect both the height reached and the horizontal distance the projectile travels. So I'm just going to sketch on the bottom. If our angle is 45 degrees, our projectile is going to do this, okay, and land somewhere over here. If it's higher than 45 degrees, our projectile is going to do this and land closer to the starting point. And if our angle is less than 45 degrees, unfortunately the projectile doesn't actually travel as far as we want it to because there's not enough y distance for it to travel before it hits the ground. Okay, so 45 degrees is the best angle for the maximum range, but again, just understand that it will affect the path of travel. So on this next slide, we actually have a motion map of this direction of motion. So on this slide, we actually have a motion map. And I'm going to show you that we're actually going to know this vector arrow. We're going to know this velocity. But when we break these apart to do the math, we want this velocity and this velocity. So in order to do this, we are actually going to use trig. So down here I'm going to write SOHCAHTOA. And if we want that green arrow, this is the adjacent leg. So we are going to use cosine. So cosine theta equals adjacent over hypotenuse. If we want to solve for the adjacent leg, we have to separate this fraction bar, and in order to do that, we multiply both sides by the hypotenuse. Because these two will cancel, and we have the adjacent leg, or the VIX equals the hypotenuse times cosine theta, or V times cosine theta. And the same thing is going to happen for the blue arrow. We have sine theta equals opposite over hypotenuse, and we want that opposite by itself, so multiply both sides by hypotenuse. These two cancel, and you have the opposite leg, or VIY equals hypotenuse times sine theta, or V times sine theta. So these bottom equations, these two, are what we're going to use in our problems. We have to split apart that initial velocity into the x's and the y's, then we can use our t-charts in order to solve for an unknown equation. So in the next video, I'm going to show you how to go through a practice problem using this information.